Imagine looking at a beaker filled with a complex chemical mixture. To the naked eye, it appears to be a single uniform liquid, but at the microscopic level, it is pure chaos. Dozens of distinct molecular structures, all tumbling and colliding in a random, erratic distribution. The core challenge of analytical chemistry is taking that chaos and pulling it apart. We need to isolate specific target molecules from this soup so we can analyze their precise structure and quantify exactly how much of them we have. We achieve this by forcing the mixture through a controlled environment and subjecting it to a literal tug-of-war between two competing physical forces. The first force is the stationary phase. This is a physical matrix, often a solid powder or a coated tube, specifically designed to grip certain molecules and hold them back as they try to pass through. The opposing force is the mobile phase. This is a flowing solvent, or a pressurized gas, that constantly sweeps over the stationary phase, trying to push those molecules forward. By deliberately engineering the chemical properties of these two phases, we dictate exactly how fast a specific molecule moves. This speed, measured as retention time, turns a molecule's invisible physical traits into a distinct, readable fingerprint. The simplest way to see this tug-of-war in action is thin-layer chromatography, or TLC. It takes this dynamic and plays it out on a flat surface based on molecular polarity. This sequence shows the basic TLC setup. A mixture is spotted on a coated plate and placed into a sealed chamber with a solvent pool. Here, the stationary silica gel coating is highly polar, while the mobile phase creeping upward, like pure hexane, is entirely nonpolar. Because like attracts like, polar molecules form strong dipole interactions with the polar silica, sticking to the plate and moving slowly. Meanwhile, nonpolar molecules ignore the silica, dissolve readily into the hexane, and travel rapidly to the top. But using a strictly nonpolar mobile phase like pure hexane often fails in practice. It is often too weak to pull compounds off the silica, leading to poor, blurred banding. To fix this, we optimize the solvent. As noted in red here, adding a slightly polar solvent like ethyl acetate increases the mobile phase's overall polarity. This creates stronger competition against the silica plate, pulling the molecules further apart. Adjusting the mobile phase is a calculated environmental adjustment designed to amplify minute differences in molecular polarity and force compounds to separate cleanly. This schematic outlines high-performance liquid chromatography, or HPLC. It takes the flat TLC plate and rolls it into a pressurized, three-dimensional steel column. HPLC relies on the exact same polarity mechanics as TLC. A mechanical pump forces the mobile solvent through a densely packed stationary phase under extreme pressure, yielding a far more precise resolution. However, in modern analytical chemistry, we frequently invert the standard polarity rules. We use a system called reverse phase chromatography. This question highlights reverse phase chromatography, asking which solvent would not be used for a C18 column. Look at the blue notes. A C18 stationary phase is extremely nonpolar. It traps nonpolar molecules, letting polar ones slip by. Because the phases must compete, if our stationary phase is nonpolar, our mobile phase absolutely must be polar. A solvent like water or methanol provides the necessary opposing force to pull molecules down the column. Therefore, the one solvent we cannot use is option C, hexanes at 81% concentration. Pump highly nonpolar hexane into a highly nonpolar C18 column, and there's no competition. The target molecules dissolve completely into the mobile phase, washing straight out the bottom at exactly the same time, yielding zero separation. If the mobile phase matches the stationary phase too closely, the entire mechanism fails. Effective separation strictly requires engineered opposition. Polarity is highly effective for liquids, but it's not the only physical property we can exploit. We can also filter molecules based on thermodynamics and volatility. This diagram illustrates gas-liquid chromatography. Here, the physical states of the phases themselves are entirely altered. The mobile phase is no longer a liquid solvent. It is an inert carrier gas, like helium. The stationary phase is a microscopic layer of liquid coating the inside of a massive coiled tube, housed inside a heated oven. Before entering that coil, the entire liquid sample is injected into a heated chamber where it is instantly flashed into a gas. Inside the column, Boiling point drives separation. Low boiling compounds stay gaseous, interacting weakly with the walls, and sweep through rapidly. Conversely, high boiling compounds prefer the liquid state, frequently condensing. This constant stopping delays their journey, yielding a longer retention time. In gas chromatography, temperature acts as the ultimate filter. We separate molecules based almost entirely on their inherent thermodynamic desire to exist as a gas rather than a liquid. Beyond polarity and volatility, there is a third major parameter we can use to break molecular symmetry: macroscopic electrostatic charge. This graphic demonstrates anion exchange chromatography, used to sort massive biological molecules. The stationary phase is a matrix of positively charged beads. As the mixture flows through, neutral or positive molecules wash into the waste, but negatively charged anions bind tightly to the positive walls. This creates a new problem. Those target anions form strong ionic bonds with the stationary phase. Left alone, they will never elute. To retrieve them, we introduce a competitive mobile phase loaded with sodium chloride. The negatively charged chloride ions flood the column, outcompete the proteins for the positive binding sites, and force our target molecules to release and flow out into the beaker. By controlling the exact concentration of that competing salt, we dictate the precise moment a specific protein loses its grip, allowing us to sort complex biological mixtures by their exact isoelectric points. Polarity in HPLC, volatility in gas chromatography, and charge in ion exchange. The hardware changes dramatically, but the governing physical law is identical. Every molecule possesses a specific partition coefficient, a mathematical ratio describing exactly how it splits its time between a mobile phase and a stationary phase. That coefficient translates directly into the primary output of analytical chemistry, the peak on a chromatogram. As shown on these handwritten axes, the specific time or volume it takes for a substance to elute defines its exact position on the graph. Retention time represents a precise mathematical output of a molecule's specific structural affinities. Analytical chemistry relies on exploiting those subtle physical desires. By engineering the perfect arena of conflict between a stationary matrix and a mobile fluid, we strip away the chaos of a mixture. We force the invisible microscopic world to accurately identify itself on our macroscopic terms.